Aliens might not be out there anymore. They might already be on their way here. Not lights in the sky, not rumours, actual machines or ships, crossing the dark right now aimed at this planet, at you. Stay with this video, because once you see how real that possibility is, you won't look at a quiet night sky the same way again. You're surrounded by a light that left its source a long time ago, not by anything happening right now. When you look at a star, you're not seeing its present, you're seeing its past, delayed by distance and the speed of light. Light travels at about 300,000 kilometers per second, around 186,000 miles per second. That's incredibly fast, but space is so large that even this speed is slow on cosmic scales. A star 100 light years away is showing you what it looked like 100 years ago, because its light needed 100 years to cross that gap and hit your eyes or your telescope. The same rule applies to everything, not just stars. If some civilization around that star built its first radio transmitters in 1920, those early signals are only reaching you now. You're getting their old news, whether that's random radio noise, early radar, or something more organised. You never see their true present, only whatever their light and radio are doing when the signal started its journey toward you. So here's the first key point. You do not see the universe as it is, you see it as it was. Every direction in the sky is a different delay. Nearby stars are a few years or decades in the past. More distant ones are centuries or millennia behind. Galaxies are millions or billions of years behind. Your idea of now simply does not exist at galactic scale. That raises a hard question. If all your information about other star systems is delayed, how could you possibly know what they are really doing right now, including whether anyone has already started moving toward you? To answer that, you have to scale up from single stars to the whole Milky Way. Your galaxy is roughly 100,000 light-years across. That means even a perfect, uninterrupted beam of light needs 100,000 years to go from one side to the other. A message from the far side of the galaxy, travelling at light speed, started its trip long before human civilization existed. A decision made there today will not be visible here for tens of thousands of years. Think about what that implies for travel. If an advanced species somewhere in the Milky Way looked at early Earth, saw a promising planet, and decided to send a mission, that decision could have happened when humans were still using basic stone tools. They could have launched slow ships or probes at a fraction of light speed, and those craft could currently be deep inside the galaxy, halfway or more along their route, while you are still seeing that civilization star as it was before they even had technology. From your point of view, that system might look quiet, ordinary, uninteresting. From reality's point of view, they already made their move a long time ago. Now, connect this to your own timeline. You call this year 2026, but that is only local time, tied to Earth's orbit and rotation. Out in space, every star is showing you a different date. A star 10 light-years away is showing you 2016. A star 50 light-years away is showing you 1976. A star 1,000 light-years away is showing you the Middle Ages or earlier. Some galaxies are showing you light that left before Earth formed 4.5 billion years ago. So any alien civilization making decisions about Earth is doing so based on an outdated version of your planet. If they are 100 light-years away, they currently see Earth in 1926, with no satellites, no internet, no spaceflight. If they are 1,000 light-years away, they might see only pre-industrial agriculture. If they are millions of light-years away, they see no humans at all, just a young world with evolving life. That means every now is mismatched. You're present, they're present, and what you see of each other are all different. When they decide, should we contact them, ignore them, or send probes, they are reacting to a past version of you. So here's the next problem. If decisions are made in one time frame, information arrives in another, and ships travel on yet another time scale, in what order do things actually show up at Earth? Do you see a "we're coming" signal first, or does the hardware get here before you ever realise anyone made that choice? A lot of people assume signals come first because they move at light speed, and ships move slower. That's only true if you're present when the signal is sent and you see it without delay. In reality, you're always behind. Take an example. Suppose there is a civilization 100 light years away. Right now, in their frame of reference, they are in the year 2126 on their own calendar. Right now, they see Earth as it was in 1926, because your light also takes 100 years to reach them. They analyze your atmosphere, maybe detect a slight change from early industry, maybe pick up the first week radio leak. They decide you are interesting and launch a probe at 10% of light speed, about 30,000 kilometers per second, around 67 million miles per hour. That probe will take about 1,000 years to get here, from 100 light years away at 1/10 light speed. But you, sitting on Earth, will not see their modern light from the year 2126 until 2226, because their updated light also needs 100 years to cross the distance. By the time you finally say, hey, that star looks more active now, their probe has already been in flight for a century, you're always catching up to things that already happened. If the distances and speeds line up differently, you can get even more extreme situations, where a fast probe launched from closer range reaches your solar system first, and the only way you know it came from that star is by working backward from its trajectory. The signal announcing the launch, the light showing advanced development on their planet, and the arrival of the hardware do not have to show up in that order. So ask yourself this: if you can be overtaken by someone else's decisions, and if ships can, in practice, beat their own news across space from your perspective, what does that say about the idea that no one is coming just because you don't currently see anything obvious in the sky? Once you accept that light carries old information, it changes the default assumption. Inside a sphere a few hundred light years wide around Earth, there are tens of thousands of stars. Over billions of years, many of them have had time to form planets, form life, and maybe form civilizations. If even one of those civilizations, at any point in its history, decided, send something to that blue planet, then there is a long interval where their ships are already in motion toward you, and you are still looking at their ancient starlight and thinking, nothing is happening. From your perspective, the sky is calm. From the timeline of the galaxy, decisions have already been made, launches already happened, trajectories already set, and some of those trajectories could intersect your orbit. You're late to the information, but right on time for the consequences. That leads to the next question. If the universe is this delayed and this big, and if you're surrounded not just by stars, but by actual planets orbiting them, how many possible launch pads for those decisions are already known? And how many more are waiting to be found? How many planetary systems did you actually know existed 30 years ago? One, just yours. The Sun, 8 planets, some moons, done. Astronomers suspected other stars had planets, but they didn't have hard proof. No images, no solid data, just models and guesses. Now look at where you are. By early 2026, astronomers have confirmed over 6,000 exoplanets, around 6,128, depending on the catalogue update, in more than 4,500 different star systems. That jump happened in just a few decades. That's not a slow, gentle change. That's a hard flip from maybe to they're everywhere. And here's the important part. These 6,000 plus worlds are not an even sample of the galaxy. They're the easy ones. You mostly find big planets close to their stars because they tug more strongly on the star or block more of its light. The two main methods, watching a star wobble from the gravity of its planet and watching the star dim slightly when a planet crosses in front of it, are heavily biased toward giant close-in planets. You're seeing the low-hanging fruit, the hot Jupiters, the big Neptunes, the super-Earths hugging their suns. Smaller Earth-sized planets, especially those farther out in the comfortable temperature zone, are harder. They block less light, they tug less. They need more precise instruments and more observing time. So if you already have thousands of confirmed planets, mostly from crude first-generation surveys and biased methods, what you're seeing now is just the visible tip of a much larger distribution. So here's the question that should tighten your stomach a bit. If you can pick up thousands of planets with relatively blunt tools in a tiny slice of the sky, how many potential launch pads are actually sitting out there when you count the whole galaxy? Because that's where the numbers start to explode. Astronomers now think that most stars have planets. Not some, not a few, but most. The old picture of lonely stars drifting through space is wrong. Data from missions like Kepler showed that planets are common, especially small ones. Statistically, when you pick a random star in the Milky Way, the default assumption is not no planets, it's there's probably a system there. Your galaxy has on the order of a few 100 billion stars. Even if you are extremely conservative and say only a fraction of those have planets, you're still looking at hundreds of billions of planets. Then narrow it down, not all of those worlds are Earth-like. Fine. Say you only care about Sun-like stars, then out of those you only care about Earth-sized planets in the habitable zone, the distance range where liquid water can exist on the surface. Now do the brutal math in words. If only 1% of Sun-like stars have one Earth-sized planet in that temperate zone, that still gives you tens of millions of potential Earths in this one galaxy alone, and 1% is pessimistic compared to some current estimates. At that point, the sentence, "maybe we're the only ones," stops sounding humble and starts sounding statistically ridiculous. Tens of millions of potentially Earth-like planets, billions of years of time, and only one technological species ever? That's not careful skepticism, that's betting against the entire dataset. So then you hit the next level of tension. It's not just that planets are common, it's that you're starting to see them in detail, deep enough that you can ask, does this world even look friendly to life? That's where the big new space telescopes come in. Instruments like the James Webb Space Telescope don't just detect exoplanets, they analyze their atmospheres. When a planet passes in front of its star, a thin shell of starlight filters through the planet's air. That light carries a fingerprint. Certain colors get absorbed by certain molecules. By splitting that light into a spectrum, you can see which gases are present. So now you're not just saying there's a planet there. You're saying this planet has water vapor in its atmosphere, or this one has carbon dioxide, or this one shows methane. You've already seen water vapor signatures on some exoplanets, especially larger ones. You've picked up the combinations of gases on hot, giant worlds that give you a sense of their chemistry, their clouds, even their temperature structure. Scientists talk about biosignatures, patterns of gases that are hard to maintain without life. For example, oxygen and methane together can be a strong hint, because they react with each other and don't like to stay in balance unless something keeps replenishing them. You're not at the point of screaming alien life from one spectrum, but you are at the point where you can say, this atmosphere looks weird, this one looks interesting, this one looks dead. That's already way beyond guessing. That is checking alien weather out to tens or hundreds of light years. And if you're already doing that for a few targets with a single big telescope, what happens when you bring in an instrument built to do this at scale? The Nancy Grace Roman Space Telescope is designed to turn your exoplanet search into a flood. It will have a wide field of view and advanced instruments, and the expectation is that it will find over 100,000 exoplanets in just a few years of operation. Not 6,000 over decades, but 100,000 in one mission phase. Think about what that means in simple terms. If you treat planets as potential launch pads for civilizations, then Roman is basically drawing a huge map of possible launch sites in your part of the galaxy. Instead of knowing about a few dots scattered here and there, you start building a dense catalogue with thousands of candidates for worlds where something interesting could have evolved long ago. Some of those worlds will be too hot, some too cold, some gas giants, some bare rocks, but a fraction will end up in the right size range, at the right distance from their stars, with the right kind of star in the right part of the galaxy. Those are the ones you will stare at harder with whatever comes after Webb and Roman, telescopes dedicated to pulling out finer and finer details from those faint spectra. So now link this back to the real question that's been building since the start. You know, planets are common. You know, Earth-sized planets in habitable zones are not exotic. You know you're about to multiply your known sample from thousands to tens of thousands or more. You know some of those planets will be older than Earth by 1 billion years or more. Given all of that, where do the odds really point? Toward we're alone, or toward they're out there and some of them had a huge head start? Once you stack the numbers, rare Earth stops feeling like a shield and starts feeling like denial. You have a galaxy with hundreds of billions of planets. You already know of thousands, with many roughly Earth-sized, some in the right temperature range. You're building tools that will add another 100,000 to your list and let you probe their air. Statistically, it becomes far more reasonable to say there are many worlds where civilizations could have arisen than to cling to the idea that you're unique. And if there are many worlds where civilizations could have arisen, you only need one that actually did, early enough, with enough stability, to move from radio to starships. One planet out of tens of millions of candidates that hit the right conditions, evolved intelligence, built technology, and then started launching probes or ships outward, over and over millions of years. From that point on, the question shifts. It's no longer, do aliens exist somewhere abstract out there? It becomes, given this many launch pads, given this much time, and given that interstellar travel is hard but not forbidden by physics, what are the chances that at least one of those worlds has already sent something into the volume of space that currently includes you? And that's where the tension spikes, because if you accept that planets are abundant, that habitable planets are numerous, and that some are much older than Earth, then aliens might already be on their way, stops being a dramatic line, and starts looking like the quiet, boring, statistically safe bet. So the next step is obvious. If there are this many potential launch pads scattered across a galaxy this old, you have to ask, which of them are not just habitable but well-placed and well-timed to send something here? And what does habitable zone really mean when you zoom out to the scale of entire galactic neighborhoods? Here's the first thing you need to lock in. Not every planet counts, only the ones that sit in a specific band around their star. Too close and surface water boils away, too far and it freezes solid. That just right band is the habitable zone, or Goldilocks zone. Around the Sun, that zone is roughly from about 0.945 to 1.4 astronomical units, around 140 to 210 million kilometers, about 87 to 130 million moon miles. Earth sits inside that strip, which is why you have stable oceans instead of a steam world or an ice ball. Liquid water is a big deal because it is an efficient chemistry lab. In liquid water, molecules move, collide, react, and build complexity. On Earth, every known form of life depends on water. So when astronomers scan those thousands of exoplanets, the first filter is simple. Is this world in the right distance range from its star to keep liquid water? If a planet is much closer than that band like Mercury, it gets hammered with radiation and heat. Its atmosphere, if it has one, gets stripped or cooked off. If it's much farther out, then any surface water is mostly locked up as ice. There can still be subsurface oceans, like on some icy moons, but for simple surface-based sunlight-powered life, the habitable zone is the main real estate. So, after seeing that the galaxy is full of planets, the next step is to ask, out of all those orbits, how many sit in these not too hot, not too cold bands, and how many of those stars sit in a good position inside the galaxy itself? Because the same logic that gives you a habitable zone around a star also gives you a kind of habitable zone inside the Milky Way. Near the center of the galaxy, conditions are harsh. You have a dense crowd of stars, more supernovae, stronger radiation fields, and the influence of the supermassive black hole at the core. Far out in the outer disk, you have fewer heavy elements, because not as many generations of stars have lived and died there. Both extremes are bad for long-term, stable, Earth-like planets. Too much radiation and chaos near the core, not enough raw material in the distant outskirts. Between those extremes, there is a broad ring where conditions are more balanced. Enough heavy elements to build rocky planets and complex chemistry, but not so much violent activity that everything keeps getting sterilized. Your solar system sits in that ring, about 26,000 light-years from the galactic center. You're not in a weird special pocket, you're in an average productive zone. That means something important. You share this comfortable band with a huge number of other star systems. You are one address among many in a strip of potentially life-friendly real estate that wraps around the galaxy. You are built from heavy elements: carbon, oxygen, nitrogen, silicon, iron. Those elements were not there in the early universe. The first stars were almost pure hydrogen and helium. They had to live, die, and explode in supernovae to create heavier elements and spread them into space. Only after several generations of star birth and death could solid, rocky planets like Earth even exist. Astronomers call the abundance of elements heavier than helium metallicity. The Sun has a certain metallicity, and when we look at stars in your local region, a lot of them have similar or even higher metallicity. That is a strong hint that many of them are capable of forming rocky planets, not just gas giants. High metallicity means more building blocks for continents, cores, atmospheres, and maybe life. Here's where the tension ramps up. Some of those Sun-like stars with good metallicity are much older than the Sun, by billions of years. The Sun is about 4.6 billion years old. There are stars a bit like the Sun that are 6, 7, even 8 billion years old. If a planet like Earth formed around one of those stars, life there would have had a huge head start. Give Earth an extra billion years, not of just existing, but of developing technology past where you are now. Think about how far you have gone in only a few hundred years, from steam engines to nuclear power, from horse-drawn carts to interplanetary probes. Now stretch that kind of progress over hundreds of millions of years. Fusion drives stop being theory and become hardware. Antimatter engines move from sci-fi to engineering. Self-replicating autonomous probes are not wild ideas, they are old infrastructure. Any civilization that started even a few 100 million years earlier than you gets a lead that is almost impossible to imagine from your point in history. They would have had time to send not just one mission, but waves of missions sweeping across large portions of the galactic disk, long before humans existed. And the last piece that ties this together is motion. None of these stars, including the Sun, are fixed in place. Every star orbits the center of the Milky Way, taking on the order of 200 to 250 million years to make one full lap. Their paths tilt, bob and drift relative to each other. Over time, your stellar neighbors change. Systems that were far away come closer, others move away again. For an interstellar civilization, that slow reshuffling is a set of windows of opportunity. When another star system passes relatively close, the energy cost to send a probe or a ship there drops. The distance is smaller, the travel time is shorter. A civilization planning missions on million-year timescales can wait for these alignments and launch when it is cheapest. Right now, your own solar system is moving through the galaxy, along with countless other stars that share the same broad orbit. You and those other systems are riding the same galactic highway. If even one older civilization somewhere along that highway uses these close passes to spread outward, then at some point, one of their launch windows lines up with you. So now the picture looks like this. You are sitting in a good stellar habitable zone inside a good galactic habitable zone, surrounded by stars with the right chemistry, some much older than yours, all slowly shifting position and sometimes drifting into useful proximity. From the point of view of a patient, advanced civilization, your region is not empty space. It is prime, well-connected real estate. The only thing left to add to this is time. How long the galaxy has been running this setup, and how many chances that gives for someone to notice you, decide you matter, and actually start moving something in your direction. The time part of this story is brutal, and you need to see it clearly, because this is where they might already be on their way, stops being a dramatic line and turns into the boring default outcome. The Milky Way is around 13 billion years old. Earth is about 4.5 billion years old. Humans with technology strong enough to throw signals and spacecraft into space are roughly 100 years into that phase. Not 100 million, just 100. Radio, rockets, electronics, that's all recent. On the scale of the galaxy, you are brand new. Lay it out in simple steps. For most of the galaxy's history, Earth didn't exist. Then Earth formed. For most of Earth's history, there were no humans. Then humans evolved. For most of human history, there was no advanced technology. Then, very recently, you invented radio, computers, rockets, nuclear power. You are right at the beginning of your technological arc, and that arc is squeezed into a tiny sliver of galactic time. Now compare that tiny sliver to what even very slow interstellar travel can do. Take a probe that moves at 0.01 times the speed of light, 1% of light speed. That's about 3,000 kilometers per second, roughly 6,700,000 miles per hour. Around 10 million times faster than a typical passenger jet. That sounds insane by human standards, but it is actually quite modest compared to the speed of light. At that pace, a probe could cross the whole galaxy, about 100,000 light-years across, in around 10 million years. To you, 10 million years feels like an eternity, but on a 13 billion year timeline, 10 million years is a small fraction. You can fit more than 1,000 of those galaxy-crossing trips inside the age of the Milky Way. That means any civilization that learns how to send long-lived probes at even 1% of light speed has enough time to send wave after wave of missions across the entire disk. Not once, but many times over. Now look at what you have already done, starting from almost nothing. Your fastest current spacecraft, Voyager 1, is moving at about 17 kilometers per second, around 38,000 miles per hour. That is only about 0.006% of light speed. At that rate, it would need tens of thousands of years just to get through the distant cloud of icy bodies at the edge of the solar system, the Oort cloud. On a galactic scale, that's nothing, but even at that slow pace, Voyager 1 has already left the heliosphere, the bubble of solar wind around the sun. It is now in interstellar space. With chemical rockets, built by a species that has only had modern technology for about a century, you've already pushed hardware out of your star's immediate influence. That tells you something important. Escape is not hypothetical. You don't need exotic physics to leave home. Even primitive technology can, given enough time, climb out of the gravity well and keep drifting. So here's the uncomfortable step. If you, this young species, with all your internal problems, can already throw a probe into interstellar space using crude engines, what do you think a civilization does if it has 1 million years of technological development behind it, or even 10 million? Your own physics says that fusion rockets are possible. Colliding light atomic nuclei like deuterium and helium-3 releases huge amounts of energy. Designs exist on paper that could push a spacecraft to around 0.1 times light speed, 10% of light speed, around 30,000 kilometers per second, something like 67 million miles per hour. Antimatter propulsion, if you could produce and handle enough antimatter, is even more powerful, converting mass to energy with far higher efficiency. None of this breaks the laws of physics. It's not magic, it is engineering difficulty. You need materials, energy, industry, and time. The barrier is practical, not fundamental. Now remember, you came up with these concepts in barely 100 years after inventing radio. In 1 century, you went from, we don't know if other stars have planets, to we've launched probes out of the solar system and designed fusion starships on whiteboards. So step back. If a civilization appears on one of those older, metal-rich, well-placed planets, and if it stays stable for 1 million years or more, it has more than enough time to build and refine these technologies to the point where sending interstellar probes is routine. On those timescales, even very slow expansion fills huge volumes of space. The galaxy doesn't need many such civilizations. One is enough to send a network of probes through large parts of the disk. Here's where the probability argument kicks in. You have a galaxy that's 13 billion years old, with tens of millions of potential Earth-like planets, some older than Earth by billions of years. You've known physics that allows interstellar probes at 1%, 10%, maybe more, of light speed. You have examples from your own history that show how fast technology can snowball once a species starts building complex tools. Combine those 3 facts, long time spans, huge numbers of potential homes, and physically possible travel speeds, and ask a simple question. Is it more reasonable to assume that no civilization has ever used those options, or that at least one has? If at least one civilization ever reached the point of building reliable interstellar probes, and if it had even a few million years of stability, then the natural outcome is a spreading front of machines, colonies, or both, moving outward from its origin. Every new outpost can, in turn, send more probes. Expansion doesn't have to be fast to be effective. It just has to continue. Once that front starts, you get a wave moving through the galaxy. Maybe it's patchy. Maybe it slows down near some regions and speeds up near others. Maybe it's not a neat sphere, but a messy network of routes along the easiest paths. The exact shape doesn't matter. What matters is that on a 13 billion year clock there is space for that wave to form, to grow, and to reach wide areas, including your local region. So the honest default is not, probably no one is travelling. The honest default is, if anyone at any time in the last few billion years cracked long-term interstellar travel and stayed around for a while, then right now, somewhere their probes are still moving, still operating, still out there. From that angle, your position becomes clear. You are a young, noisy civilization, only about a century into the radio and rockets phase, living in a galaxy that has had more than 10 billion years for someone else to get started. The wave, if it ever began, doesn't care that you only just arrived. It's been expanding on its own schedule. And here's the tension point. If such a wave exists, there is no special reason it would politely wait for you to be ready before it passes through your sector. It might have crossed your region long before humans, leaving only old probes or subtle traces. It might be just arriving now. It might be a few thousand years away. But under these timescales, the strange position is not to say no one's coming. The strange position is to act as if motion never happens in a galaxy this old, this full of worlds, and this compatible with interstellar engineering. The next question is obvious and sharp. If travel at 1% or 10% of light speed is enough to sweep the galaxy in manageable chunks of time, and if you already know how to sketch those drives on paper, then what do the actual machines look like that someone older than you would build? And how would you recognize one if it was already inbound? Your current rockets feel huge and loud, but on a galactic map they barely move. A Saturn V can throw a crew to the moon, about 380,000 kilometers away, 240,000 miles, in a few days, and that feels like a big deal from the ground. Now, spread out the scale, Proxima Centauri, the nearest star after the Sun, is about 4.24 light-years away, roughly 40 trillion kilometers, around 25 trillion miles. If you pushed a Saturn V-style chemical rocket on that route and somehow kept it fueled, you'd be waiting tens of thousands of years for arrival. That gap explains a lot in one hit. Chemical rockets are fine for hopping around one star system. They are useless for serious interstellar work. The energy you get from burning fuel with oxygen is tiny compared to what you need to keep accelerating a ship to meaningful fractions of light speed. So if anything is coming toward you from another star, it is almost certainly not riding on anything like a 20th century moon rocket. So the next question is simple. If chemical rockets are too weak for the real distances, what kind of propulsion actually makes sense for crossing the space between stars? The first answer most serious designs land on is fusion. Fusion is the process that powers stars, combining light nuclei like hydrogen into heavier ones and releasing huge amounts of energy. On paper, a fusion rocket that uses deuterium and helium-3 as fuel can heat its exhaust to extreme temperatures and throw reaction mass out the back at very high speeds. If you can build and control that, you can, in principle, push a ship to around 0.1 times the speed of light, 10% of light speed, about 30,000 kilometers per second, roughly 67 million miles per hour. At that speed, Proxima Centauri is not a tens of thousands of years problem anymore. It becomes a trip on the order of 40 years. That's one human working lifetime or half of one, and on a civilization timescale, that is nothing. Projects like Daedalus and Icarus are not fiction pitches, they are serious engineering studies by human scientists who sat down and asked, using known physics and realistic materials, what would a fusion starship look like? The fact that you can even sketch these designs a century after inventing radio tells you how reachable 0.1c actually is for someone with more time, more resources. If fusion is one track, the next one uses a different trick. Don't carry your energy, shine it at the ship from far away. Light sails do exactly that. You build an extremely thin reflective sail, much lighter than a typical spacecraft, and you push it using photons, either from a star or from a massive focused laser array. Each photon carries momentum, and over time a constant push adds up. If the sail and payload are light enough and the laser is strong enough, you can keep accelerating for a long time. For very small payloads, gram-scale chips with cameras and antennas, the numbers get wild. A powerful ground or orbital laser can push a tiny sail to around 0.2 c, 20% of light speed, about 60,000 kilometers per second, something like 134 million miles per hour. At that speed, a probe aimed at Alpha Centauri can cross the gap in just over 20 years. That's less than the age of many satellites you already have in Earth orbit. Your own Breakthrough Starshot concept is built exactly on this idea. A swarm of tiny, almost bullet-like probes, launched by a laser array, no onboard fuel, just a sail and electronics. These things would pull enormous acceleration, hundreds or thousands of G, far beyond what a human could survive, but the hardware can tolerate it. The point here is simple. You're already planning systems that would send hardware to another star in a human career timescale. A more advanced civilization could scale this up or optimize it or run it continuously. Once you accept that, the next step is obvious. If you can do it with sails and lasers, what happens when a civilization uses the most energy-dense fuel known to physics? Antimatter is the mirror version of normal matter, and when matter and antimatter meet, they annihilate and release their entire mass as energy. Fusion only converts a small fraction of mass into energy. Antimatter reactions effectively convert almost all of it. In rough terms, antimatter engines can be up to around 100 times more efficient than fusion in pure energy per unit mass. Handling antimatter is hard. You need intense magnetic fields and careful storage, because contact with normal matter means instant energy release. But none of that is impossible in theory, it's just extreme engineering. An advanced civilization with large energy budgets and massive infrastructure could build engines that use antimatter as a primary or secondary stage, blasting a ship up to very high fractions of light speed, well beyond 0.1 c. At those speeds, the Milky Way's 100,000 light-year size stops looking like a wall and starts looking like a very long but very finite route. A crossing at half-light speed is still centuries, but for machines, or for a culture that thinks in millions of years, that is tolerable. For shorter hops between nearby stars, trip times drop into decades or less. For an interstellar network, that is manageable. Now tie this straight back into the big question you care about. What does all this do to the idea that aliens might already be on their way? You, a young species, can already draw up multiple propulsion methods that reach 0.1 to 0.2 times light speed without breaking any known physical laws. Fusion drives, light sails, laser arrays, antimatter, coronas around magnetic nozzles. These are all sitting in human documents right now. They are not refined. You haven't built them full scale, but the roadmaps exist. So the idea that no older, richer civilization sitting on a stable planet in a good part of the galaxy, with millions of extra years to play with, has ever moved from paper designs to real hardware starts to look weak. Once a society builds even one working interstellar drive, they can send a probe. Once they can send one probe, they can send many. It may start slow, but over time they can spray probes in all directions, sampling stars, mapping planets, checking atmospheres. From that point onward, there is always some future time when one of those probes, or one of the larger ships that follow them, is heading straight for the region of space your solar system happens to be in. It might be far away in time, it might be soon, but the combination of possible drives and huge timescales makes no one is moving the strange conclusion, not the safe one. So the next layer of tension is this. If fast, advanced ships and tiny laser-pushed probes are the realistic tools for crossing between stars. Have you already seen something like that and not recognized it? And what kind of object should you be looking for if one of those incoming machines is already somewhere in your outer sky? How sure are you that you would even recognize the first thing from another star that slipped through your backyard? In 2017, you got a test of that, and the honest answer was not very sure at all. That year, astronomers spotted an object later named 1I/Oumuamua. It was moving too fast on the wrong kind of path to be a normal asteroid or comet bound to the Sun. Its orbit was hyperbolic, which means it came in, swung around the Sun and headed back out, never to return. Its speed was tens of kilometers per second, and at the closest approach to the Sun, it was moving at about 88 kilometers per second, roughly 197,000 miles per hour relative to the Sun. That is not the speed of some rock gently falling inward. That is the speed of something that came in from deep space with serious momentum. So your first confirmed interstellar visitor was not a spaceship you could photograph in high detail. It was a small, dim object you almost missed, blasting through the inner solar system on a one-time pass. You saw it late, tracked it briefly, then watched it vanish. Here's the uncomfortable part. The more you looked at it, the stranger it got. Based on how its brightness changed as it tumbled, Oumuamua didn't behave like a roughly round asteroid. The light curve suggested an object maybe around 100 meters long, but only tens of meters across, so something like a long, thin slab or cigar shape, maybe a football field in length, over 300 feet, but much narrower. That is already odd, because most natural objects that size are more lumpy and compact, not extremely stretched out. Then you saw its motion wasn't purely gravitational. After it passed the Sun, it showed a small but real, non-gravitational acceleration, the kind of extra push you see from comets when gas jets out from their surfaces. But Oumuamua did not show the normal comet behaviour. There was no visible coma, no tail, no obvious gas cloud. It looked like a rock, but moved like something getting a very gentle, continuous push from some process you could not clearly see. So you were stuck with a weird combo, strange shape and strange motion. That led to a split in interpretation. Most scientists favoured natural explanations because that's the correct default. Maybe it was outgassing some kind of volatile ice you don't usually see, like hydrogen or nitrogen, which wouldn't show up as a visible tail. Maybe it was a very low density, fluffy object, a kind of frozen foam with a huge surface area for sunlight to push on, so radiation pressure could account for the acceleration. Those explanations stretch what you've actually seen before, but they remain within nature's toolbox. However, the fundamental fact doesn't change. You have now seen at least 2 confirmed interstellar objects, Oumuamua and 2I/Borisov, and you probably miss many more. That means your solar system is not isolated. It is constantly getting peppered by material from other star systems, rocks, ice, debris, and if natural processes can throw rocks across interstellar space, then an engineer can throw probes the same way, riding on the same kinds of trajectories. So here's the next hard question. With data this thin, how would you actually tell the difference between a weird rock and someone's discarded hardware? With Oumuamua, you never got close-up images. At its closest, it was still more than 30 million kilometers away, over 20 million miles. To your best telescopes, it was just a point of light, a dot. You inferred shape and rotation from how that dot brightened and dimmed over time, not from any resolved picture. If you take that limitation seriously, it leads to a simple, slightly scary conclusion. If Oumuamua had been a long-dead alien light sail or a derelict framework, or the husk of a probe whose system shut down ages ago, you would not have been able to tell from the data you had. It would still show up as a faint dot with a weird brightness pattern and an odd acceleration curve. Your instruments were not set up to inspect it in detail. Your detection came late and your follow-up time was short. That is the low-resolution problem. For most fast, small interstellar objects, you get a handful of pixels, some spectra, and a short tracking arc. You're trying to decide rock or probe from data that barely distinguishes rock or blur. If that's the level you're working at now, then you have to accept the possibility you may already have watched alien-made objects pass through the inner solar system without realizing it, because the data was never good enough to push you out of the weird natural object comfort zone. So what changes that? How do you move from lucky, late detections to systematic surveillance that can actually catch the next strange visitor early enough to study it properly? This is where upcoming survey telescopes matter. The Vera Rubin Observatory, for example, is designed to scan the entire visible sky regularly, night after night, building a deep, dynamic map of everything that moves or changes. It will spot many more interstellar interlopers, not one every few years, but potentially a steady stream. With that kind of system in place, you start building statistics. You see how many interstellar visitors come through, what speed ranges they use, what kind of sizes and brightness patterns they show. Most will probably be normal debris, weird but explainable. But if even one object shows an acceleration profile that cannot be pinned on outgassing, or a spectrum with materials that look manufactured, or a maneuver that looks like a controlled change in course rather than a passive drift, then the conversation changes overnight. At that point, you're forced to treat at least some of these rocks as possible derelict probes, hardware from a civilization that may not even exist anymore, thrown out into the galaxy long ago, still drifting, still following old trajectories. Your solar system stops being just a gravitational pit that catches random stones and becomes a place where the leftovers of someone else's expansion phase occasionally fall through. And if you accept that the next Oumuamua-like object you see might not be dumb rock, but dead hardware, the obvious next step is to ask, what about hardware that isn't dead? What about probes that are not just drifting through but are actively looking at you? Maybe not in the inner system, but parked quietly in the dark further out, already here, already watching. Right now, a growing bubble of your own noise is racing away from Earth at the speed of light, and there is nothing you can do to stop it. For about a century, you've been leaking radio into space without any plan, just as a side effect of technology. Early AM broadcasts, old TV signals, military radar, air traffic control, satellite links, deep space communications, all of it goes out in every direction. Radio waves move at light speed, about 300,000 kilometers per second, roughly 186,000 miles per second, so your oldest signals are now roughly 100 light years away. That means there's an expanding sphere about 200 light years in diameter with Earth at the center that contains your entire accidental broadcast history. Inside that volume are tens of thousands of stars. Any civilization in that region with receivers better than yours already has evidence that something strange happened recently around a yellow star in the Orion Arm. So the basic question is, how visible is that bubble really? Is it just a faint background hiss? Or is it a clear "we are here" stamp for anyone who knows how to listen? Most of your transmissions are weak and spread out. A lot of TV and radio signals are broadband, unfocused, and get drowned in cosmic noise as they travel. Over light years, they fade into the background. But not all of your signals are like that. Some transmissions are extremely powerful and tightly aimed. Planetary radar systems, the ones that ping asteroids and map planets, fire short, intense pulses. Spacecraft links use narrow beams to send data over billions of kilometers. Compared to normal radio chatter, these are bright spikes. A civilization with radio telescopes more sensitive than yours could, in principle, pick those spikes out of the noise. They could see that in a tiny patch of sky, a star that used to be quiet suddenly started producing structured narrowband radio bursts over a short period of time. From their point of view, that is a very specific signature. Stars don't suddenly start doing that on their own. Planets don't suddenly start doing that on their own either. Technology does. One conclusion stands out, something with machinery is powered up there. If leakage and radar are the accidental part, then you've also gone a step further and shouted on purpose. On top of the background noise, you've sent intentional messages like the Arecibo broadcast in 1974 aimed at a star cluster about 25,000 light-years away. Encoded with a simple pattern describing numbers, atoms, a human figure. You've done other messaging extraterrestrial intelligence attempts too, tightly focused transmissions beamed at specific stars. Those messages are like address labels stuck onto your radio bubble. They say, in effect, yes, this wasn't an accident. There is an intelligent source here, and here is proof that we can do math and build transmitters. They are small compared to the full volume of leakage, but they are precise high-power markers. So now you have to ask, if your signals are already out there, and if they are detectable to someone more advanced, how long does it actually take for that to turn into a physical response? Take a concrete case. Think about a civilization 50 light years away. Your earliest strong radio leaks reach them around now, plus a few decades, because there's fixed 50-year delay. Say on their calendar, they detect your activity in the year you would call 2050. They analyze the signal, confirm it's artificial, and realize there is a young technological species around that star. They don't have to reply with radio. They can wait, think for 50 years, run models, argue, decide what they want to do. Then they launch a probe at 0.2 times light speed, 20% of light speed, about 60,000 kilometers per second, roughly 134 million miles per hour. At that speed, a 50 light-year trip takes about 250 years. Total timeline from their first detection to probe arrival at Earth's orbit, about 300 to 350 years. On human timescales, that's several generations. On cosmic timescales, it is essentially instant. Your current actions, your radio, your radar, your deliberate messages can already be setting up decisions that will result in hardware appearing in your sky a few centuries from now, long after you and everyone you know is gone, but well within the lifespan of your civilization, if you manage not to wipe yourselves out. Once you see that, the situation stops being theoretical. You are not a hidden, quiet planet. You're a source of high-energy, structured radio sitting in a galaxy where physics absolutely allows other species to build interstellar probes. So you have to be honest about your behavior. You're acting like a camper yelling and lighting flares in a dark forest, but telling yourself the forest is empty because you don't see anything moving between the trees. You have no guarantee that it's empty, and the only real data you have is that you're making noise. That radio bubble is not a metaphor. It is a physical structure, a shell of signal fronts moving outward through space, measured in trillions of kilometers, trillions of miles. Anyone inside that shell with the right equipment can, in principle, detect you, classify you, and file you away under active. If any civilization has been running a long-term sky survey, mapping radio bubbles around different stars, then Earth is already on their chart. In their database, your planet is not just a world with oxygen, it is a world that turned its transmitters on about a century ago. In other words, technologically emergent, potentially interesting, potentially dangerous, worth a closer look. And that brings you straight to the next tension point. If you've already lit yourself up across tens of thousands of nearby stars, and if technosignatures like this are exactly the kind of thing you're starting to search for around other systems, then you have to flip the perspective. What signs are they leaving that you can see? And what happens to your whole worldview if you catch just one clear signal that someone else has already gone beyond radio and into full galaxy-scale engineering? You've already made it clear to the galaxy that you're noisy. The next step is asking a sharper question. Not, is there life? But, is there technology? Life leaves chemical fingerprints. When you look at a planet's atmosphere, you can see gases like oxygen, methane, and other complex organics. On Earth, oxygen is constantly topped up by life. Methane has strong biological sources too. A mix of certain gases kept in balance can be a biosignature, a sign that something alive is working in the background. But advanced civilizations don't just change their air by breathing, they change it by building. That's where technosignatures come in. These are not just this world might have life signals, they are someone here is running machine signals. Narrowband radio that looks engineered, intense laser flashes, industrial pollutants like CFCs in a planet's atmosphere, extra heat from giant structures trapping starlight. All of these are technosignatures. Right now, you're only at the beginning of a serious hunt for these. You've spent decades chasing biosignatures in theory and starting to look for them in practice. Technosignatures are just now moving from interesting idea to planned search strategy. But in principle, they are easier to spot because nature doesn't usually produce perfectly tuned radio, coded laser pulses, or chemicals that only factories make. So why haven't you already picked up a clear signal? For a long time, the main search for technosignatures has been Radio SETI, the search for extraterrestrial intelligence. Projects under the SETI Institute and other groups have pointed radio telescopes at selected stars and scanned slices of the sky, looking for narrow, structured signals that stand out from natural noise. If an alien civilization beams a focused radio message in your direction, that's one of the places it could show up. So far, SETI hasn't produced a signal everyone agrees is artificial. You get odd blips, short-lived events, things like the famous wow signal, but nothing that holds up under repeat checks. Some people take that as proof that no one is out there. That's a mistake. You have to look at how small your search really is. The radio spectrum is huge, the sky is huge, time is huge. You've only scanned a tiny fraction of the relevant frequencies, directions, and time windows. It's more honest to say you've taken a very small sample and found nothing yet. That doesn't tell you what's going on across a whole galaxy, it only tells you that no one has sent an obvious strong broadcast on the exact channels you've checked during the brief periods you were listening. Radio is just one angle. If a civilization goes big with its energy use, you can look for something even harder to hide: waste heat. A star pumps out energy in all directions. A civilization that builds massive solar collectors or structures around its star, often called Dyson-style constructs, will intercept some of that energy and then re-radiate it at longer wavelengths, mostly in the infrared. The star plus structure system would look too bright in the far infrared compared to how it looks in visible light. Telescopes that scan the sky in infrared can look for stars with this kind of excess. If you found a star that behaves in a way only huge engineering projects can explain, that would be a technosignature. That would be evidence of a Kardashev Type 2 level civilization, one that taps a large fraction of its star's power. A society that can do that has no problem building and tossing out interstellar probes the way you casually launch satellites into Earth orbit. For them, sending a mission to another star is routine infrastructure, not a heroic one-time event. And remember the laser-pushed light sails you already talked about. Those are not only a propulsion system, they're also a technosignature. A star-to-star transport network based on light sails needs huge laser arrays. Those lasers would be extremely bright at specific wavelengths, turned on for long periods, sometimes in repeated bursts as ship after ship is accelerated. If such beams are active in a system and happen to line up with your line of sight, your instruments could see them as intense, narrowband flashes or continuous spikes, much brighter than anything natural at those exact frequencies. So if aliens are running their own version of breakthrough starshot on a grand scale, your telescopes might not see the probes, but they might see the beams that launch them. The highway lights are visible even if the cars are too small to track. This brings you to the key point that changes the emotional weight of the search. You don't need a sky full of obvious signs, you don't need hundreds of independent detections, you need one. One strong, repeatable, unnatural radio pattern from a star system that cycles in a way natural sources don't. One planetary atmosphere spectrum with a clear set of industrial chemicals that cannot be produced in bulk by the geology or biology. One star whose dimming and brightening over time matches stable, sharp-edged occultations, the kind you'd expect from structured panels or swarms, not from dust clouds. One unambiguous technosignature is enough to prove that the universe makes technological civilizations. Once you have that proof, the whole game changes. It's no longer, maybe intelligence is a freak accident and we're alone. It becomes, we know technological species exist, and at least one of them made it to the point of messing with planetary atmospheres or star-scale infrastructure. From that moment on, the conservative position is not, no one has launched anything. The conservative position is, if they can build this, and they have had millions of years, they probably sent probes. You don't have to assume invasion fleets. You just have to assume that a culture that can engineer at that scale is curious, cautious, and long-lived enough to look around. And when you combine that with everything you've already seen, billions of planets, millions of potential Earths, huge timescales, possible propulsion systems, and your own loud radio bubble, there's a clear line. Once you confirm that at least one such civilization has existed, the idea that none of them ever launched anything in your direction becomes the wild claim. The simple straight-line conclusion is that some of them did, which leads directly to the next uncomfortable question. If sending radio back and forth over light years is slow and clumsy, what is the smarter move for a truly advanced civilization that notices a new, noisy planet light up and wants to watch it, understand it, and maybe talk to it on its own timetable, instead of waiting centuries for replies? Why would any advanced civilization sit there waiting centuries for a radio reply when they can just drop a robot in your backyard and let it handle everything? That's the core of the Bracewell probe idea. Ronald Bracewell pointed out that using radio alone for contact is a terrible strategy if you care about time. You send a message, it crosses light years, you wait decades or centuries, then maybe you get a reply, then you wait again. Meanwhile, everything on both ends is changing. A smarter move is to ship the intelligence to the target system. You build an autonomous probe, load it with sensors, long-lasting power, and serious software, then send that instead of a conversation. It arrives in the destination system and parks itself somewhere stable, maybe in a wide orbit, maybe around a distant moon, maybe in deep space on a long, slow path. From there, it listens, it monitors radio noise, spectra, any artificial emissions. It studies the planets, moons, and asteroid belts. It can sit silent for as long as it needs, hundreds of thousands of years if necessary. And when it finally detects a spike in technology, sudden radioactivity, nuclear tests, satellite launches, it already has a front row seat. It can then decide if and when to speak up and in what language based on what it has learned. That's a very different picture from two planets yelling across light years with radio and hoping they sync up. Radio has one advantage: it's cheap to send, you turn on a transmitter and you're done. But it's slow, and it's dumb in the sense that the message can't adapt once it's on its way. A Bracewell-style probe is expensive up front, but once it's in the target system, it can think, adapt, update in its behaviour and respond quickly. Picture one sitting out near the Kuiper belt in your own system, orbiting at 40 to 50 astronomical units, about 6 to 7.5 billion kilometres from the Sun, roughly 4 to 5 billion miles. From there it can watch the outer planets, see your spacecraft going to Jupiter and Saturn, pick up radio traffic leaking from Earth, and track your rocket launches. It doesn't wait decades for signals to bounce back and forth. It sees everything in near real time, with only the light speed delay across the solar system, a few hours at most. If you're an advanced civilization trying to manage risk and maximize information, that is a better setup. You keep your main population safe, far away. You expose only a small expendable probe. If the locals are violent or unstable, you lose hardware, not a homeworld. If they are interesting, you get detailed, continuous data. So then comes the next question. If someone had done this to you, how hard would it actually be for them to hide their probe? From interstellar distances, stealth is surprisingly easy. Your telescopes are good for big, bright, hot objects. A small probe, a few meters across, painted dark with a surface temperature only slightly above the 2.7 Kelvin cosmic microwave background, is almost invisible in infrared. It doesn't glow much, it doesn't reflect much. Even within the solar system, the brightness of such an object would be tiny. It would be fainter than many of the asteroids you currently track. Unless it passes right in front of a bright background star, or right across a telescope field while you're looking, you're not going to notice it. It could sit in a lazy orbit in the outer system for millions of years and never once show up as a confirmed there is an artifact here detection in your surveys. A cold probe tucked into a stable orbit around a distant Kuiper belt object would just blend into the noise. As far as your current instruments are concerned, it might as well not exist. That leads straight into an uncomfortable reality check. How hard have you actually looked? You've done some searches around Earth for large artificial objects, focusing on near-Earth orbit and regions where you keep satellites. You've scanned the inner solar system for asteroids that could pose an impact hazard. There have been a few targeted searches for odd orbits or objects that might be artificial, but a comprehensive, fine-grained survey for alien probes across the whole solar system, that doesn't exist. The volume from the orbit of Neptune to the inner edge of the Oort cloud is enormous, thousands of times the volume of the inner solar system where Mercury, Venus, Earth and Mars live. It is filled with small icy bodies, dust and dark rocks. Your detailed coverage of that space is effectively zero. You only know a thin slice of what's out there. So the honest statement is, you do not know that there are no probes here. You just haven't really checked. Now push the idea one step further, and the tense you've been using starts to look wrong. You keep saying already on their way, as if ships are just now crossing the void toward you. But in a Bracewell scenario, the important arrival might have happened long before humans showed up. In that setup, a civilization millions of years older than you scans the galaxy, flags young star systems with promising planets, and seeds them with probes. Those probes drift in, break, park themselves in stable orbits, and go quiet. They might have done this when Earth was still covered in early forests, or before mammals evolved, or even before complex life took off. For most of that time, you wouldn't qualify as interesting. No radio, no cities, no rockets, just a changing biosphere. The probes watch, but they don't act. Then, in a tiny slice of time, your last 100 years, your technology curve explodes. You go from no flight to space stations, from no radio to global communication networks, from no nukes to thousands of warheads. From the probe's perspective, that's a clear trigger. The slope of your change goes vertical. Suddenly the local species has tools that can alter its biosphere, damage its environment, and eventually reach space in a serious way. That might be the moment on its internal timeline where it flips state from observe silently to prepare contact, or, in a darker scenario, to notify origin and await instructions. In that case, the real contact event is not when a huge ship appears in your sky. It's when one of those quiet probes decides that you've crossed some threshold and starts transmitting, maybe to you, maybe back home, maybe to other probes. The crucial decision to engage happens here, in your system, based on data it has been collecting for a long time. So instead of they might already be on their way, the more disturbing version is they might already be in position, just not talking yet. And once you let that thought in, another one follows naturally. If probes and machines can sit and wait for the right conditions before making a move, what about life itself, down at the microbial level, hitching rides on rocks and comets between stars, setting the stage for civilizations long before any probes are built at all? You've been talking about probes and ships, but there's a more basic question sitting underneath all of that. How did life even start here? And are you sure it started here at all? Asteroids and comets don't just orbit politely forever. In young crowded systems, big planets tug them around, stars pass nearby, and gravity slings some of that debris completely out of the system. A close encounter can give a rock just enough extra speed, a few kilometers per second, thousands of miles per hour, to climb out of a star's gravity and keep going. At that point, that rock is not just a rock anymore. It's a tiny, slow spacecraft. No engine, no guidance, but it is on an interstellar trajectory carrying whatever was trapped inside it when it left. So the next question is obvious. If a piece of a planet or a comet core leaves its home system with microbes buried a few centimeters under its surface, do those microbes die quickly in deep space, or can some of them hang on? Tests in low Earth orbit give you a rough answer. Some life is much tougher than you'd like to think. Experiments on the International Space Station have shown that certain bacteria, spores of fungi, and even some plant seeds can survive for years in space conditions, as long as they have a bit of shielding, a crust of rock or dust. Tardigrades, those tiny water bears, can tank vacuum, radiation, and extreme cold then revive later when conditions improve. That doesn't prove microbes can ride a rock from one star to another and still wake up, but it does prove that multicellular life on Earth already includes organisms that can endure the basic ingredients of that trip for at least short stretches. Tough spores buried deeper could last longer. DNA can be damaged, but heavy shielding and dormant states extend the clock, now add time, a lot of time. Interstellar rocks do not need to be fast by Starship standards. Take a rock travelling at 5 kilometers per second, about 11,000 miles per hour. That's slow compared to light, but it is enough to drift 1 light year in about 60,000 years. That sounds huge to you, but on billion-year timescales, 60,000 years is a tiny slice. Over the age of the galaxy, billions of years, countless rocks, comet fragments, and ice chunks can be kicked out of systems, drift through interstellar space, and pass near other stars. Each pass by a planetary system is a chance, a small one, but non-zero, for that rock to get pulled in, heat up, fragment, or impact a planet or moon, and dump its internal cargo into a new environment. So you end up with a slow, diffuse, but relentless mechanism. Stars form planets, planets get hit, debris gets ejected, debris wanders, and occasionally gets captured elsewhere. In that picture, stars act like slow pollinators, trading material across the galaxy over immense spans of time. Life, or at least the chemistry that leads toward life, might not be locked to one world. It might be moving very slowly but surely from system to system. If that can happen naturally, you have to ask a sharper version. What happens when someone does it on purpose? That's where directed panspermia comes in. Instead of waiting for random impacts to throw rocks into space, a technological civilization could package hardy microbes deliberately in shielded capsules and fire them at target systems. You pick worlds that look promising, maybe in the habitable zone, maybe with the right chemical mix, and you seed them. You already research ultra-resistant spores and ways to harden DNA against radiation. You think about how to make life more durable for medicine, for industry, even for long-term storage. The same tools, pushed harder, could design life specifically to tolerate deep space, layer it in protective shells, wrap it in ice, aim it with rockets or electromagnetic launchers, and you have a way to pre-terraform worlds at a basic biological level. In that scenario, life on Earth might not be purely local. It could in principle be part of someone else's large-scale project, a side effect of a civilization that wanted to fill the galaxy with the starting kits for evolution. They might be gone now. The garden could have outlived the gardeners by hundreds of millions of years, but the results, biospheres like yours, would still be here. And then the link back to civilizations becomes clear. If simple microbes can survive inside rocks for long journeys, or inside engineered capsules for even longer ones, then complex hardware has a much easier job. A probe with solid shielding, self-repair systems, and good thermal control is in a far better position than a dormant bacterium stuck under a random layer of stone. Microbes riding comets and asteroids show one thing. The galaxy already runs a slow natural courier system. Material routinely gets ejected, crosses into a stellar space, and sometimes ends up in other systems. That proves the transport channel exists. A civilization doesn't need to invent the route, it just needs to learn to use it. You can piggyback on that infrastructure. You can park probes on long-lived cometary orbits that eventually cross other stars' paths. You can hitch rides on gravitational slingshots that rocks already use. You can send tiny passive payloads that take millions of years to arrive, but cost you almost nothing once they're launched. So if you know that nature already moves rocks, and potentially life between systems over long timescales, then it's a small step to accept that any civilization with patience and basic engineering can move more complex things the same way, more reliably and more often. And that loops you right back into the central tension. If life itself can travel between stars, seeding worlds over and over, then the number of planets where intelligent species could arise goes up again, and the amount of time those species have had to send their own machines out increases too. The seeds come first, the civilizations come later, and once those civilizations appear, they're playing on a board that was already connected long before they built their first radio tower. So if the galaxy has been quietly swapping microbes and chemistry for billions of years, and some of those seeds grew into technological societies, then the next question hits hard: why don't you see those societies everywhere? And what kind of brutal filters might be in place that decide which ones survive long enough to reach you, or for you to ever notice them at all? There's a brutal way to look at the galaxy that cuts through a lot of the maybe they're friendly talk, and you need to hear it clearly. The dark forest idea says this: every technological civilization is sitting in a dangerous environment with very little information. You don't know who is out there, you don't know what they can do, you don't know how they think. You only know two things: resources are finite, and other civilizations might decide you're a threat. In that kind of setting, shouting your position is not brave, it's stupid. So the logic runs like this: if you're smart and cautious, you do not broadcast your location to the whole sky. You keep your emissions low, you avoid big, obvious technosignatures, you probe others quietly rather than lighting up beacons. Anyone who makes a lot of noise, anyone who announces, "Here we are, we're growing and we're building big technology," is a potential risk. Maybe they stay peaceful, maybe they don't. You don't get a safe guarantee. In that framework, every civilization is like a hunter who knows there may be other hunters in the dark. You don't walk around yelling, you move quietly, you observe, and if you see someone else stand up and start firing, you think hard about eliminating them before they can eliminate you. Translate that out of metaphor and into physics. What you're really talking about is energy. A star system that suddenly starts blasting out high-power radio, running megawatt or gigawatt lasers, building invisible megastructures, and throwing big reflective objects into orbit, is changing its signature. From quiet background noise to something sharp and obvious. To anyone scanning for threats, that looks like a system where a young species just turned on heavy industry and long-range tools. Those energetic signatures are targeting information. They give you exact coordinates, rough technological level, and a growth curve. If you are an older, more paranoid civilization, that's all you need to mark them as watch closely, or even neutralize early. The easiest target to hit is the one that can't hit back yet. This is why the dark forest view is so uncomfortable, because when you apply it to Earth, you see that you are already doing exactly what a cautious species would tell you not to do. You are not quiet. High-power planetary radar beams slam out into space, advertising your location. Deep space communication dishes send sharp, focused signals toward probes and spacecraft. You have sent deliberate hello messages, knowing they will leak into the sky far beyond the target. Your militaries run powerful over-the-horizon radar systems, blasting short, intense pulses. All of that folds into the radio bubble you already heard about. Inside a radius of roughly 100 light-years, anyone with better instruments than yours can, in principle, see that a previously dark star has started emitting narrow-band, pulsed, structured radiation. In dark forest terms, you're not the quiet hunter, you're the noisy newcomer, setting off fireworks and hoping no one in the trees cares. Now connect that to the question of incoming visitors. If someone out there is playing by dark forest rules, how do their probes behave when they arrive here? They are not going to drop into low Earth orbit with huge reflective hulls and announce themselves on every frequency. A probe sent under that strategy would be small, low power and cautious. It would stay in deep space or in a distant orbit, maybe out near the Kuiper Belt or parked in a Lagrange point where your detection coverage is weak. It would observe, map your infrastructure, record your languages, follow your data traffic, and build a detailed risk profile of your civilization. From their perspective, the contact event already happened when they detected your radio bubble and decided you were worth the cost of a probe. Everything after that is monitoring, analysis, and planning. Whether you notice them or not is almost irrelevant to them. If they're following dark forest logic, they don't want you to notice. From your side, nothing official has happened yet. There are no ships in the sky, no clear signal, no landing. You still think you're alone, but if this model is right, that gap is intentional, not accidental, and this is where the stakes jump. Up to now, you might have pictured aliens on the way as explorers, scientists, maybe even tourists. Under dark forest logic, that is the optimistic case. The pessimistic case says some of those incoming craft are not explorers at all. They're insurance policies. A cautious long-lived civilization might look at any new technological species as a possible future competitor, especially one that starts burning fossil fuels, building nuclear weapons, and experimenting with AI and nanotech. The safest move, from their point of view, is not to wait and see if you stay peaceful forever. It's to get assets into your system early, so that if you ever look like a real threat, they can act quickly and decisively. That could mean pre-positioned weapons, systems designed to quietly sabotage your infrastructure, or just detailed targeting data ready to pass to something heavier that follows later. You don't know because you don't even know if they exist. That uncertainty is exactly why dark forest logic is so harsh. It says, if you can't know their intentions, but you do know they can hurt you, then revealing yourself is dangerous. You, right now, are revealing yourself. You are doing it without a plan, without a consensus, and without any idea who might be listening. So when you think about the phrase already on their way, you have to widen it. It might not mean a shiny ship heading straight for a landing. It might mean silent probes already in your outer system sent long ago, feeding your behavior into some remote decision-making process. And if that's even a possibility, then the next logical step for any serious, cautious civilization is obvious. Don't send fragile biological crews at all. Send machines that can survive for millions of years, repair themselves, copy themselves, and spread through star systems quietly and efficiently until the entire galaxy is threaded with their presence. Right now, even with your limited tech, you've already made one quiet but very important decision. You trust robots more than you trust sending people. Look at your own missions. Mars rovers, Venus landers, probes to Jupiter, Saturn, Pluto, the outer solar system. They're all machines. No air, no food, no water, no life support, just power and hardware. Humans need thick shielding against radiation, controlled temperature, gravity solutions, huge amounts of consumables. Robots need a power source, a thermal design, and replacement parts if something breaks. At interstellar distances, that difference is massive. So ask yourself this: if you already default to robots for anything risky and far away, what do you think a civilization a million years ahead of you is doing? For them, AI probes are the obvious tool. You build a machine with sophisticated software, strong materials, and a long-lived power source, and you send that instead of a crew. No life support, no fragile bodies, no psychological issues. If it fails, you lost hardware, not citizens. If it succeeds, it sends back terabytes of data and maybe even prepares the way for something bigger later. Now push that idea into its logical next step, because just sending robots is only the beginning. The real game changer is self-replication. A von Neumann probe is exactly that. A machine designed to use local materials to build copies of itself. You send one to a target system, it slows down, enters the system, and heads for resource-rich regions like asteroid belts or icy bodies loaded with water and other volatiles. Once there, it mines metals for structure, silicon for electronics, volatiles for propellant and chemistry. Using factories built into itself or modular systems it assembles, it constructs one or more children probes. If one probe can build 2 copies in, say, 100 years, and each of those can do the same, you get exponential growth. So run that in plain language. Start with 1 probe. After 100 years, you have 2. After another 100 years, you have 4, then 8, 16, 32, and so on. After 10 cycles, you're at 1024. After 20 cycles, you're over 1 million. After 30 cycles, you're over 1 billion. Even if you're much slower, even if you only double every few hundred years, over a few million years, the numbers go through the roof. And remember what you already said about timescales. A few million years is a short slice of galactic history. You can fit thousands of those windows in the age of the Milky Way, so a single civilization that manages to build robust self-replicating probes and keeps them running has enough time to seed enormous parts of the galaxy with its machines. Now ask a very simple resource question. Is there even enough stuff out there to support something like this? Look at your own solar system. The planets are not the only game. You have asteroid belts full of rock and metal. You You have Kuiper belt objects and comets full of ice and organics. You have small moons, trojans, scattered disk objects. Even if you ignore the gas giants and just look at solid material, there is enough metal and silicon and carbon in your system to build staggering numbers of small probes. Scale that up to the entire Milky Way, hundreds of billions of stars, each with their own planets, belts, clouds, and debris fields. The resource base for machines is enormous. A civilization doesn't have to strip planets bare. It can live off small bodies, mine a tiny fraction of what exists, and still feed self-replicating swarms indefinitely. And energy? Stars throw out more energy than any single species could ever use. Solar panels, fusion reactors, even tapping into accretion disks or other exotic sources, all of that is available in principle. From an engineering standpoint, once you have a functioning von Neumann design, the galaxy is not empty. It's a dense field of fuel and parts. So what do these things actually look like if they're out there? Self-replicating probes don't need to be big. In fact, smaller is better for stealth and efficiency. You could have main factory units meters across, and secondary survey units centimeters across, or smaller. At those sizes, against the background of natural debris, they are practically invisible. A swarm of such probes could enter a system like yours, spread out and quietly map everything. They could measure every orbit, scan every moon, analyze every atmosphere, and log artificial emissions, all without ever being large or bright enough to stand out as obviously artificial in your current survey data. At most, you might see a faint glint that gets catalogued as small asteroid, unknown orbit, then lost in the noise. From your perspective, the system would still look empty. From their perspective, it would be fully instrumented. Now you hit the key question. Is any of this forbidden by physics? Because if it's not, then the probability arguments kick in again. Nothing in your current understanding of physics blocks self-replicating machines at nano to meter scales. You know how to build solar panels, batteries, electronics, robotic arms, 3D printers, and mining hardware. You research self-repairing materials, autonomous manufacturing, and AI that can manage complex tasks with minimal supervision. The hard parts are integration, robustness, and time. If you had a few more centuries of development and a unified push to build such a system, you could plausibly launch primitive von Neumann-style probes yourself. Not science fiction, just extreme engineering. So from a purely engineering standpoint, self-replicating probes powered by local solar energy, using local materials, are possible. Difficult? Yes. Impossible? No. Given that the big conditional is simple, if any civilization in the last few 100 million years reached the point of building such systems and actually deployed them, the natural expectation is that their wave has already passed through, or at least reached your region by now. The fact that you don't currently see clear evidence of them might say less about their absence and more about your limitations. Your telescopes are optimized for other goals. Your search efforts are narrow. You haven't systematically swept the outer solar system for centimeter to meter scale objects on odd orbits with weird spectra. You've barely started thinking about what a stealth swarm would look like in your data, so the tension stacks again. You live in a galaxy where self-replicating machine swarms are physically possible, resource feasible, and brutally effective over long timescales. You're late to the party. If anyone launched such a system long ago, you're likely living inside the tail end of its spread right now, whether you recognize it or not. And that leads directly to the next hard layer of this story. If the galaxy can be filled with self-replicating probes, and if life and intelligence can spread across billions of years, then maybe the reason you don't see visible empires everywhere is not that they never existed, but that most of them hit hard barriers, filters, before they lit up the sky in a way you can easily detect. Which means that if you do ever see clear evidence of ships or probes from another civilization, they're not just proof that aliens are real, they're proof that at least one species made it through those filters, and that has serious implications for what they're like and what might be waiting ahead for you. You've just stacked the odds in favour of a busy galaxy, huge time spans, millions of Earth-like worlds, travel that's hard but not impossible, and yet your sky looks quiet. That gap is the Fermi Paradox in plain language. If civilizations are common and can move between stars, why don't you see clear signs of them everywhere? One serious answer is that most of them never get that far. They run into great filters, big steps or disasters that wipe them out or keep them stuck before they ever light up the galaxy. A filter can be a physical barrier like life almost never starts, or a self-inflicted catastrophe like they always blow themselves up once they invent nukes. Either way, the result is the same. The galaxy stays visually quiet, not because no one ever appears, but because very few make it past the dangerous phases. So you have to ask, are the hard filters mostly behind you or mostly ahead of you? Start with the optimistic version. Maybe the really rare parts already happened. The birth of life from non-life might be incredibly unlikely. Maybe it took a perfect combination of chemistry, temperature, and time, and even then was a freak event. Or the step from single-celled life to complex multicellular organisms might be the bottleneck. On Earth, that jump took billions of years. Intelligence with technology might be another rare roll of the dice. If any of those are truly low-probability events, then technological civilizations might be extremely rare. You might be one of only a handful in the entire galaxy, or even the observable universe. In that case, the reason you don't see anyone else is simply that there aren't many, and most are far away or not overlapping with you in time. In that filters behind us scenario, you're already through the worst part. You're not guaranteed to survive, but you've cleared the steps that almost no planets manage to clear. That makes you statistically precious. Any other technological civilization that spots you might see you the same way, not as just another noisy species, but as an extremely rare outcome, something worth protecting or at least observing carefully. Now flip it to the pessimistic side, the filters might be in front of you. Look at your current situation honestly. You have nuclear weapons that can end industrial civilization in hours. You have climate systems you're pushing hard without fully understanding, driving long-term changes in temperature and sea level and weather patterns. You're building more powerful AI systems fast while worrying in public about losing control of them. You can engineer pathogens, tweak biology, and spread things globally in days by accident. If the real great filters are exactly these kinds of steps, then most civilizations that reach your level don't die because life is rare. They die because power outruns wisdom. They invent tools that can crash their environment or destabilize their societies faster than they can build safety systems and global coordination. They show up as a loud, short flash in radio or infrared, then go dark. In that filters ahead of us scenario, the galaxy could have seen many technological sparks flare up and then vanish again. A few get lucky or disciplined and build stable systems that handle nuclear risk, climate risk, AI risk, and bio risk. They invest in redundancy, off-world habitats, interstellar spread. Those are the ones that last, and those are the only ones you're likely to ever meet. Now here's where incoming ships or probes become more than just cool aliens. If you ever get clear, unambiguous evidence of an alien probe in your solar system, or a ship in your sky, you will know at least one civilization made it past its filters. That is terrifying and encouraging at the same time. Terrifying because they will be far beyond you in technology, organization, and long-term planning. Encouraging because their existence proves something critical. It is possible to get through the lethal phase without wiping yourself out. They will not be a random sample of all civilizations. They will be biased. By definition, any civilization that manages to operate starships for millions of years without disappearing has solved problems you are still flailing around with. Their ethics, their strategies, all of that will be shaped by one core constraint: do not die. That means they could look cold and strict by your standards. They might enforce heavy control on their own tech, tightly regulate dangerous research, and build harsh safeguards. They might have rules about contact that prioritize their survival over your comfort. They may have zero patience for species that stay chaotic and unstable once they reach high power levels. So when you think about aliens already on their way, don't picture a random group of explorers. Picture the survivors, a civilization that has passed through its own age of nuclear weapons, climate stress, AI accidents, and biotechnological risks, and came out the other side still functioning. That culture will have tested defense systems, refined policies, and long memories of close calls. In that light, any ship or probe that reaches you carries a double message. On the surface, it says, "We exist and we can cross the distances." Underneath it says, "We found a way through the filters that you are only starting to face." That's the grim comfort. Their presence means the universe doesn't always hit delete. It doesn't guarantee that you will make it, but it proves that making it is not impossible. Somewhere, somehow, a species managed to solve or sidestep the traps that might be waiting for you. At the same time, it also means they understand exactly how dangerous a young, rapidly advancing civilization can be. They will have thought hard about preemption, about containment, about how to interact with emerging powers without letting them become existential threats. Some of the ships already on their way in that scenario might not be scouts in the friendly sense. They might be part of a long-term security strategy. So you end up with a sharp, uncomfortable conclusion. If you ever do meet aliens, they will almost certainly be the ones who already passed the tests you're just now walking into. They will arrive as both a warning and a proof of concept, a living demonstration that survival is possible, and a reminder that from their perspective, your species is still in the most dangerous, least predictable part of its timeline. And that raises one more critical question. If the galaxy has had billions of years to produce these survivors, and if their ships and probes move on long-planned trajectories, then why does the timing line up so that now feels like the moment when paths might cross? What is it about this exact slice of cosmic time that makes your emergence, your radio bubble, and any incoming trajectories overlap? Your solar system is not parked in space, it's moving, and so is everything else. Stars orbit the center of the Milky Way. They bob up and down through the galactic disk. They drift past each other over tens and hundreds of millions of years. The neighborhood around the sun is not fixed, it churns. That means something very simple but very important. The place where Earth is now is not where Earth was, and not where Earth will be. Your whole solar system traces a long path around the galaxy, roughly one full orbit every 200 to 250 million years, at a speed of around 220 kilometers per second, about 490,000 miles per hour, relative to the galactic center. So if a civilization somewhere else wanted to send ships that cross tens or hundreds of light years, they would not aim at where you are today. They would aim at where your system will be when those ships arrive. A launch that left 1 million years ago can easily be targeted at future Earth's orbit, not present Earth's orbit. From your side, it looks like something just shows up. From their side, it was planned far in advance. That's the first timing piece. Paths cross because the stars are constantly moving, and someone with enough knowledge of those motions can plan for future intersections. Now think about what you can already do with orbital mechanics. Right now you can predict where planets, moons, and spacecraft will be years or decades from now with high precision, often with errors of only a few kilometers or miles. You routinely plan missions that arrive at Mars at the right second, or meet up with asteroids years in the future. You solve those trajectories with computers using gravity, thrust, and time. Extend that idea. With better data on how stars move in the galactic potential, and better models, you could in principle predict where entire star systems will be millions of years from now. You'd treat stars as moving targets in a three-dimensional grid. A more advanced civilization, with better telescopes, longer baselines, and more computing power could do exactly that. To them, launching toward Earth is really launching toward the future position of this system when our ship arrives. They are playing long-lead targeting, not on the scale of months, but on the scale of millions of years. If you can already hit a moving planet on a timescale of years, it's not a stretch to accept that someone else can hit a moving star system on a timescale of epochs. So timing isn't random, it can be engineered. But launches don't need to be constant, they can be triggered. The galaxy has its own breaking news events. Supernovae, gamma-ray bursts, large impacts, sudden or weird changes in a star's brightness, rearrangements in planetary systems. These are visible across long distances. A star that suddenly brightens and then settles into a different pattern stands out. A planet's atmosphere that suddenly fills with dust, smoke, or industrial chemicals stands out. If you are an advanced civilization monitoring the sky, these events are alerts. Something changed here. A big star exploded there. A planet's atmosphere on that system shifted in a way that suggests a massive impact, or maybe industry, or maybe a biological bloom. You don't need to send missions everywhere all the time. You send them in bursts when you see something that looks important, dangerous, or interesting. That means the timing of launches depends on triggers. For some systems, the trigger might be a supernova that threatens a region. For others, it might be a planet that suddenly shows a sharp rise in greenhouse gases or artificial pollutants. For Earth, one obvious trigger stands out. From the outside, for billions of years, Earth was just one more living world. Its spectrum showed water, oxygen, maybe some methane, seasonal changes in vegetation, but nothing that screamed technology. Then, in what geologists call an instant, everything spiked. In just a few centuries, you changed atmospheric chemistry, increasing CO2 and other industrial gases. You covered the night side of the planet with city lights. You started launching satellites that flash and move in predictable orbits. You lit up the radio band, building that expanding bubble of structured noise. On a plot of technological activity versus time, Earth's line is basically flat for billions of years, then shoots almost vertically upward in the last few hundred years. To you, that's history. To someone watching from far away, that's a ping, a clear on signal. A star that had a quiet, natural-looking planet now has a planet that glows oddly at night, leaks radio, and shows industrial fingerprints in its air. If any monitoring system is out there, this is the moment you get flagged. This system just turned the lights on. Watch it. For some civilizations, that may be all they do, mark you and keep collecting data. For others, that ping may be the exact threshold that triggers a launch window. Now pile the statistics on top of that. You're dealing with millions of potentially habitable systems across the galaxy. Their development start times are spread over billions of years. Some biospheres died early. Some are ahead of you. Some are behind you. Some might be roughly parallel. Each of those worlds, if it gives rise to a technological species, will have its own ping moment, its own steep rise in detectable activity. Each advanced civilization that emerges gets a certain number of launch windows, times when distances, energy, and triggers line up so that it makes sense to send probes or ships. They won't all choose the same targets and they won't all survive, but the total number of chances is huge. So when you combine all of that, moving stars, long lead targeting, trigger events, and millions of potential actors, you land on a simple probability question. What are the odds that none of those launch windows across all those systems and all that time line up so that right now in your era, no ships at all are in transit toward you? Given everything we've walked through, that probability is not just small, it's absurdly small. You're a young, noisy civilization in a good region of the galaxy, lighting up your atmosphere and radio bands in a way that stands out. You exist in a galaxy old enough for others to have appeared billions of years before you, with physics that allows interstellar flight at a fraction of light speed. Under those conditions, no one is coming, no one ever aimed anything here, and nothing is currently in motion in our direction, is actually the extreme claim. The default, boring, statistically safe assumption is the opposite. That at least one civilization has, at some point, fired hardware onto trajectories that intersect your orbit, and that some of that hardware is already in transit, or already here. So by the time you reach this point in the argument, aliens might already be on their way, is not a dramatic twist, it's the null hypothesis. The real question isn't are they coming, it's what exactly happens on the day you finally notice one of their machines, and how does your world react when they might be out there turns overnight into they are real, they are here, and they've been planning this longer than your entire technological history? The first real sign that something alien has arrived will probably look boring, not cinematic. It won't be a black triangle over every city, it'll be a tiny line of data that doesn't fit. A star tracker on a satellite might flag a point of light that moves in a way no known object should. A ground telescope might catch a strange reflection in high Earth orbit that doesn't match any catalogued debris. A radio telescope might pick up a narrow signal with a slow, steady drift that doesn't match any satellite you've launched. The first vehicle you actually detect could be the size of a car or a washing machine or a suitcase. A compact bus-sized bus parked in a weird orbit. A boxy object sitting in a high-inclined path that costs too much fuel for your own hardware but seems effortless for it. You notice it because engineers are obsessive, because some analyst somewhere goes, hang on, this shouldn't be here, and it shouldn't be doing that. So the first stage of arrival is not awe, it's confusion. You don't know it's alien, you just know it doesn't fit your normal lists, and that's exactly when the information imbalance kicks in. Any incoming probe has had years, maybe decades, maybe centuries to watch you. Long before it gets anywhere near Earth, it can sit in the outer solar system and read your emissions. It can measure your atmosphere and watch your CO2 levels climb. It can log your launch history, the cadence of your rockets, the distribution of your satellites. It can estimate your radar sensitivity and optical tracking coverage. By the time you notice it, it already has a detailed model of your capabilities and your blind spots. It knows how fast you can respond, what ranges your missiles cover, what orbits you patrol heavily, and what regions you ignore. Knows what languages you speak, what frequencies you use, how your internet is structured. You, on the other hand, will be trying to answer basic questions under time pressure. What is its orbit exactly, and has it been here longer than you think? What is its mass? Can you infer density from how sunlight and radiation push it? Is it spinning or holding orientation? Is it radiating waste heat or is it ultra cold? Does it maneuver even slightly in ways that rule out a dead rock or random debris? Does it respond if you ping it with radar or lasers, or does it ignore you completely? In other words, they come in with years of recon, you start from zero. That imbalance shapes every scenario that comes next. In the best case, the first arrivals are not threats at all, they're archivists. Autonomous surveyors built for long missions whose job is to sample biospheres and cultures and categorize them. Seen that way, you're not a target, you're a data point. That kind of probe might dip into your system, maybe into high orbit, maybe into a stable point like Lagrange 1 or 2, and spend some time capturing everything it can. It records your radio and TV archives. It scrapes your open data, your languages, your art, your music, your scientific journals. It studies your DNA, your ecosystems, your disease history. Maybe it deploys micro drones to grab samples of soil, air, ocean water, and human environments. It might never speak. It might not send any recognizable message to your governments or your public. From its perspective, mission success is to learn silently, compress what it saw into a robust storage format, and then either leave or wait for pickup. You become one entry in the catalogue, this is what developed on this planet at this time record in a museum that spans thousands of worlds. That outcome is almost insultingly neutral. You don't get a grand welcome to the galactic community, you get filed. But it means no one rearranges your orbit, no one shuts you down. You keep doing what you're doing with the added fact that someone else now has a copy of your entire story. The worst case looks very different. In a hostile scenario, the first visible objects are scouts for a civilization that treats biological planets as resources, or threats, or both. They may not assign moral value to you at all. To them, you're another chemical system that might get in the way of their projects later. They might decide that the safest course is to neutralize you before you ever leave your system in force. To that kind of actor, a probe might come loaded with tools that are not just cameras and spectrometers. It could map your power grid for vulnerabilities. It could probe your communication networks for weak points. It could deploy tiny secondary units into cislunar space or high orbit to sit and wait for a signal to act. In that framework, the changes you fear most, altered orbit, stripped moons, a sterilized biosphere, might not even be their primary goal. Those might be side effects of a large engineering project. Maybe they want to mine your asteroid belt at industrial scale. Maybe they want to adjust your star's output with structures that happen to disrupt your climate. Maybe they're setting up a relay hub and your planet is just in the way. From your point of view, that's horror. From theirs, it's logistics. You are the rounding error in someone else's long-term planning. The truth is likely to sit somewhere between pure archivist and pure predator, but the key point is that you don't choose which one shows up. The galaxy's filters and timelines already selected for whatever they are. Now take one more step that people don't like to think about. If ships are on their way toward you now, then in a few thousand years, you could be the ones doing this to someone else. Look at your curve. If you don't wipe yourselves out, your technology will keep compounding. Fusion power, heavy automation, advanced AI, off-world habitats, asteroid mining, those are all on the table. Spread that out over thousands of years and Interstellar probes stop being a theory and start being a line item in a long-term plan. At some point, if you survive, you will point a telescope at a distant world and see it flicker, see it light up with fires, or early cities or crude radio. You will see their ping the same way others might be seeing yours now, and then your descendants will have to decide, do we send probes? Do we stay quiet? Do we interfere? Do we protect? Do we preempt? To that younger world, you will be the ancient aliens. Your drones or ships or self-replicating machines will be the mysterious visitors. Your choices about whether to archive or to exploit will shape their entire future. That's the real shock embedded in all of this. The wave of civilizations moving through the galaxy does not end with you, it passes through you. Right now you sit on a planet about 150 million kilometers, 93 million miles from a medium-sized star, thinking of yourselves as local, recent, small. But in cosmic terms, you're in an extremely narrow high-voltage instant, the brief moment where a species goes from being confined to one rock to having the tools, the physics, and the awareness to step into that larger flow. If aliens are already on their way, or already here, then you are not at the beginning of the story, you're in the middle of one ongoing process. The spread of life and intelligence across the galaxy. Whether you end up as a footnote, a museum entry, a warning sign, or a full participant depends on what you do next, while the first faint anomalies in your data stream start to whisper that you are no longer alone. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.